Somewhere something incredible is waiting to be known. Carl Sagan.
The universe is an immense and enigmatic cosmos that has captivated humanity for millennia. With its boundlessness and grandeur, the ancient peoples, gazing up at the starry skies with reverence and wonder, laid the foundation for an endless quest to understand what lies beyond our world. We observed the movement of celestial bodies, sought to comprehend their cycles and patterns, built astronomical observatories, and created myths to explain the origin of the universe and our place within it. Each generation contributed to this ceaseless pursuit, passing down accumulated knowledge and a profound sense of awe at the majesty of the cosmos to future generations.
Over time, our tools for understanding the universe became more sophisticated. Technological advancements have allowed humanity to peer into the farthest reaches of the cosmos, to witness the light from distant galaxies, and to observe the birth of star systems. We have learned to use telescopes, satellites, and space probes to explore space, revealing many mysteries hidden within the vast expanses. Yet, as we discover more, new questions arise, questions that are even more complex and profound. What is the universe? How did it come into existence? What role does humanity play in it?
These questions remain relevant today, despite all the achievements of science and technology. Modern cosmology is a science that not only unveils the mysteries of the universe's origin and evolution, but also helps us understand the nature of time and space, the forces that govern galaxies, stars, and planets. At the core of these studies lie the fundamental laws of physics, which explain how the initial singularity, known as the Big Bang, gave birth to the universe approximately 30. This moment, filled with energy and matter, marked the beginning of everything we know, the beginning of time, space, and all that fills the cosmos.
From chaos emerged structure, stars and galaxies within which planets eventually formed, one of which became our home. Despite our insignificance on the cosmic scale, humanity has always strived to understand its place in this vast expanse. We are but specks in the infinity, yet within our minds and hearts burns a desire for knowledge. How did life arise on Earth? Are we alone in the universe? What future awaits humanity? These questions present not only scientific, but also philosophical challenges, prompting us to contemplate the meaning of existence and humanity's role in the cosmic scale. Throughout history, we have sought answers to these questions. Yet each answer we find leads to new mysteries. We see stars that extinguished millions of years ago, observe galaxies that we will never approach, and realize that our lives are but a fleeting moment in the infinite chain of events occurring in the universe. In this text, we will embark on a fascinating journey through the vastness of space, from the origins of the universe to its possible end. We will explore how our understanding of the cosmos has evolved, what discoveries scientists have made, and what questions remain unanswered. We will also seek to understand humanity's place in this infinite universe, and how our understanding of space can influence our future. In this journey, we will consider not only scientific aspects, but also the philosophical and cultural implications of our discoveries, striving to comprehend what it means to be human in such a vast and mysterious world. Space is not just the void between stars, it is an ocean of time and matter, where every atom of our bodies was born in the hearts of distant stars. Understanding this connection to the cosmos opens up new horizons, driving us to further exploration, new discoveries, and perhaps a re-evaluation of our place in this grand cosmic order. We embark on this journey not only to seek answers, but also to experience the beauty and grandeur of the universe, to realize our connection to it, and to find inspiration in its boundlessness.
The universe we inhabit is a grand and awe-inspiring object of study. It is home to billions of galaxies, each containing billions of stars and an incalculable number of planets, comets, and asteroids. Everything we see and everything that exists is governed by the same physical laws that describe the behavior of matter and energy. But how did this vast and complex structure come into being? The question of the universe's origin remains one of the most profound and intriguing mysteries of modern science.
According to the prevailing theory, our universe emerged from a state of extremely high density and temperature around 13.8 billion years ago in an event we refer to as the Big Bang. The Big Bang is not merely an explosion in the conventional sense, rather, it represents the moment when space and time as we know them began to exist. At this moment, all matter and energy were concentrated in a single point, known as a singularity. This state was so extreme that the physical laws we use to describe everyday reality could not be applied. Gravity, electromagnetic forces, strong and weak interactions, all these fundamental forces existed in a form that we have yet to fully comprehend. It was a moment of pure potentiality, a moment when everything that exists today was in a latent state waiting to be born.
From this singularity, the universe began to expand, and this expansion continues to this day. This process can be imagined as the incredibly rapid inflation of space, where every point moves away from every other point, similar to how points on the surface of an inflating balloon move away from each other. It is crucial to note that this expansion is not happening within pre-existing space. Rather, space itself is expanding. This distinction highlights the uniqueness of the Big Bang as an event that initiated not only matter and energy but also the very concepts of space and time.
Initially, immediately after the Big Bang, the universe was incredibly hot and dense. Temperatures reached trillions of degrees, and matter existed in a form with no modern analog. In these conditions, elementary particles such as quarks and gluons were in a state of free movement, forming a kind of soup. These particles interacted with each other constantly, being created and annihilated until the temperature gradually dropped to the point where quarks could combine to form protons and neutrons, the building blocks of atomic nuclei. Something remarkable was occurring. From the primordial chaos and disorder, ordered, structured matter began to emerge.
Within the first few minutes after the Big Bang, processes of nucleosynthesis began, leading to the formation of the first nuclei of light elements, such as hydrogen and helium. These processes occurred under conditions where the density and temperature were so high that individual nuclei could collide and fuse, forming heavier elements. This initial nucleosynthesis concluded relatively quickly, leaving behind a universe primarily filled with hydrogen and helium, along with trace amounts of lithium and other light elements. These light elements became the foundation for the subsequent formation of stars, galaxies, and all the structures we observe today.
It is important to note that this process was not random. It followed specific physical laws that operated with incredible precision and predictability, creating the conditions necessary for the formation of complex structures from the primordial material. Thus, the Big Bang not only marked the beginning of everything that exists, but also laid the groundwork for the development of the universe as we know it.
One of the key pieces of evidence for the Big Bang theory is the existence of the cosmic microwave background radiation, CMBR. This radiation, a sort of echo of the Big Bang, represents the relic light left over after the universe cooled and became transparent to photons. In the first moments after the Big Bang, the universe was opaque to radiation due to its high density and temperature. Photons, particles of light, constantly collided with electrons and other particles, unable to travel freely. However, about 380,000 years after the Big Bang, the temperature dropped to the point where protons and electrons could combine to form neutral hydrogen atoms. This process, known as recombination, made the universe transparent to light. From this moment on, photons were able to move freely, and this radiation, which we observe today as the CMBR, became a sort of photographic imprint of the early universe.
The CMBR reveals that the universe was nearly homogeneous in its early stages, with very slight density fluctuations. These fluctuations are believed to have been caused by quantum processes occurring during the moment of inflation, and eventually became the seeds for the formation of galaxies and star systems that we observe today. These small density variations became the regions where gravity began to concentrate matter, leading to the formation of the first stars and galaxies. The discovery of the CMBR in 1965 by Arno Penzias and Robert Wilson was a crucial confirmation of the Big Bang model and provided scientists with a deeper understanding of the early stages of the universe's development. Detailed study of the CMBR using modern satellites such as COBE, WMAP and Planck has allowed us to create an accurate map of the early universe, measuring its age, composition and density. These data confirm that the universe is indeed expanding and that its history began with the hot, dense state we call the Big Bang.
While the Big Bang theory gives us a general picture of the universe's origin, it does not explain all the details. For example, it cannot account for why the universe appears homogeneous and isotropic, that is, the same in every direction on large scales. Questions related to the flatness, homogeneity and lack of magnetic monopoles in the universe remained unresolved within the framework of the classical Big Bang theory. To address these issues, the inflationary theory was proposed, which suggests that in the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion known as inflation.
Inflation was a brief but extremely powerful period of expansion, during which the size of the universe increased by trillions of times in a minuscule amount of time. This process smoothed out any initial irregularities and made the universe nearly uniform in all directions. Without inflation, different regions of the universe located far apart from each other would not have been able to agree on their properties, as the speed of light limits the exchange of information between them.
However, inflation explains how these regions could come to such an agreement, despite their distance. Inflation resolved several problems of the standard Big Bang model. First, it explained the homogeneity and isotropy of the universe, as during inflation, any initial inhomogeneous distribution of matter and energy was smoothed out. Second, the inflationary theory provided an explanation for the origin of the density fluctuations that led to the formation of structures such as galaxies and galaxy clusters. These fluctuations arose from quantum fluctuations, which were stretched to macroscopic sizes during inflation.
Additionally, the inflationary theory predicts the existence of primordial gravitational waves, ripples in space-time that could have been generated by this rapid expansion. The search for traces of these waves in the CMBR is one of the tasks of modern cosmology and could be key to confirming or refuting the inflationary model.
Inflation also opens the door to deeper questions about the nature of the very beginning of time and space. What caused inflation? What conditions led to its initiation and termination? How are these processes related to quantum gravity and possible theories of everything? These questions remain subjects of active research, and their resolution could lead to a new understanding of not only the universe's origin, but also the fundamental laws of nature.
Thus, the Big Bang and the subsequent inflation laid the foundation for the formation of our universe as we know it. This beginning, filled with both revealed mysteries and new questions, is only the first step on a long journey that scientists continue to explore, striving to understand both the universe itself and our place within it.
After the period of inflation ended, the universe continued to expand, but at a much slower pace. This stage can be seen as the beginning of a long process during which the universe began to take on its modern characteristics. Space was still filled with hot and dense gas composed of elementary particles, which were just beginning to form into more complex structures. It was during this phase that processes began leading to the emergence of atoms, stars, galaxies, and other cosmic objects that we observe today.
Approximately 80,000 years after the Big Bang, the temperature of the universe decreased to the point where protons and electrons could combine to form neutral hydrogen atoms. This process, known as recombination, marked a significant milestone in the history of the universe. Before this moment, free electrons hindered the propagation of light, and the universe was opaque. However, after recombination, photons could travel freely, leading to the emergence of the cosmic microwave background radiation (CMBR), which we observe today.
Recombination also led to the formation of the first helium atoms and traces of lithium. These light elements form the foundation for the subsequent formation of stars and galaxies. It is important to note that at this stage, the universe was primarily a dark place, not in the sense of the absence of light, but in the sense of the absence of visible structures. It is believed that this was the beginning of the so-called Dark Age of the universe, when light had not yet been emitted by the first stars and space was filled only with rarefied gas and dark matter.
Even during this time, important processes were occurring. Dark matter, which does not interact with ordinary matter electromagnetically but exerts gravitational influence, began to concentrate in dense regions, forming a sort of skeleton for future galaxies. This process of gravitational contraction of matter into dense regions became the foundation for the formation of the first stars and galaxies. Several 100 million years after the Big Bang, the first stars began to form. These stars, known as population 3 stars, became the first sources of light in the young universe. They consisted almost entirely of hydrogen and helium, since heavier elements did not yet exist. These stars were much more massive and brighter than modern stars, with masses exceeding hundreds of solar masses, and their lives were short and turbulent. Population 3 stars played a key role in the processes of nucleosynthesis, enriching the interstellar space with heavier elements such as carbon, oxygen, and iron. These elements, known as metals in astrophysics, became the basis for the subsequent formation of planets and more complex chemical compounds necessary for the emergence of life. These early stars also contributed to the ionization of hydrogen in the surrounding space, a process known as the epoch of reionization. Reionization was the process in which the ultraviolet radiation from the first stars and galaxies ionized neutral hydrogen, splitting it into protons and electrons. This process ended the Dark Age and ushered in a new era where visible structures, stars, galaxies, and galaxy clusters began to form. Reionization was an important stage in the evolution of the universe, as it laid the foundation for the formation of the first galaxies and large-scale structures we observe today. As population 3 stars evolved and ended their lives in powerful supernova explosions, they enriched the surrounding space with heavy elements, creating the conditions for the formation of subsequent generations of stars. Population 2 and Population 1 stars, which make up most of the stars observed today. These subsequent generations of stars became the building blocks for the formation of galaxies, such as our galaxy, the Milky Way. As the universe continued to expand, gravity played a key role in the formation of large-scale structure. Gravitational forces led to the contraction of matter into dense regions, where galaxies, galaxy clusters, and superclusters began to form. In these regions, new stars formed, and the interstellar space filled with gas and dust, creating the conditions for the birth of planetary systems.
The formation of galaxies and large-scale structures in the cosmos is a complex and multi-stage process involving gravitational interactions, collisions, and mergers of galaxies, and the dynamics of dark matter. Dark matter, which makes up most of the mass in the universe, created gravitational wells into which ordinary matter was drawn, forming galaxies and their clusters.
Modern astronomy observes various types of galaxies: spiral, elliptical, and irregular. These forms reflect the complex processes of mergers, interactions, and the evolution of galaxies. Spiral galaxies, like our Milky Way, have beautiful spiral arms where stars actively form from clouds of gas and dust. Elliptical galaxies, on the other hand, are older and more tranquil systems where star formation has nearly ceased. Irregular galaxies have chaotic shapes and are often the result of gravitational interactions or mergers with other galaxies. Galaxy mergers are an important process that significantly impacts their evolution. When two galaxies collide, their stars and gas clouds begin to interact, which can lead to bursts of star formation, the formation of new star clusters, and even changes in the galaxy's shape. In some cases, a merger can lead to the formation of an elliptical galaxy from two spirals. For example, our galaxy, the Milky Way, likely formed from the merger of several smaller galaxies and continues to evolve through the accretion of matter and star systems. In the future, our galaxy will collide with the neighboring Andromeda galaxy, and this collision will lead to the formation of a new, larger galaxy that may become elliptical or lenticular. The development of galaxies and large-scale structures is one of the key processes in the evolution of the universe, and it continues to be studied by astronomers worldwide. Observations made using powerful telescopes like Hubble and James Webb help scientists not only peer into the distant past of the universe, but also understand how it will evolve in the future. These studies give us insight into how the universe gradually evolved from the hot and dense state characteristic of the Big Bang to the grand and complex structure we observe today.
The evolution of the universe is a process that continues, and we are part of it. Understanding this process helps us better comprehend our place in this vast and ever-changing cosmic order.
The question of whether life is unique to Earth or widespread throughout the universe is one of the most exciting in modern science. Life as we know it requires certain conditions to exist, such as the presence of liquid water, specific temperature ranges, and a particular chemical composition. However, on the scale of the universe, these conditions might be found in the most unexpected places. There are billions of stars, each potentially hosting its planetary system, and while conditions on most of these planets are likely unsuitable for life, even a small percentage of habitable worlds opens vast possibilities for the existence of extraterrestrial life. Earth is the only known place where life exists. The emergence of life on our planet remains one of the greatest mysteries of science. How did life arise from non-living matter? This question has occupied the minds of scientists for centuries. It is believed that life on Earth originated approximately 3.5 to 4 billion years ago, during a period known as the Hadean era. At that time, Earth was a hot, volcanically active world with an atmosphere rich in carbon dioxide, methane, and ammonia. Despite these extreme conditions, chemical processes occurring in the oceans and atmosphere created the conditions for the emergence of the first organic molecules. The process of life's origin involves several key stages. The first step was chemical evolution, during which simple molecules such as water, methane, ammonia, and carbon dioxide began to form more complex organic compounds, amino acids, nucleotides, and lipids. These molecules could have formed through various natural processes, such as electrical discharges, ultraviolet radiation, or thermal energy, for example in deep-sea hydrothermal vents. The next critical stage was the aggregation of these organic molecules into more complex structures, proto-organisms capable of self-replication and metabolism. This stage is the most mysterious, as the exact mechanisms that led to the emergence of the first self-replicating systems are still unknown. However, it is believed that RNA molecules, which are capable of both storing genetic information and catalyzing chemical reactions, may have played a crucial role in this process. Over time, these simplest organisms became increasingly complex, passing through stages of evolution that led to the emergence of prokaryotes, then eukaryotes, and eventually multicellular organisms. These changes occurred over billions of years, resulting in the vast diversity of life forms we see today, from microorganisms to complex organisms such as plants, animals, and humans. The origin of life on Earth is also closely tied to the evolution of the environment. The question of life beyond Earth has been a subject of discussion and speculation for centuries. With the advancement of science, this question has become the focus of serious research. Today, scientists actively study various objects in the solar system and exoplanets located in habitable zones, where conditions might be suitable for life. Mars, for instance, has long been considered one of the most likely candidates for harboring life. Recent missions, such as the Curiosity and Perseverance rovers, are exploring the planet's surface for signs of ancient life, such as organic molecules and geological structures indicating the presence of water in the past. Although the surface of Mars today is cold and dry, there is substantial evidence that liquid water may have existed on the planet in the past, a key condition for life. Geological data suggests the existence of rivers, lakes, and possibly entire oceans in ancient times, which could have created favorable conditions for microbial life. Moreover, the moons of the giant planets, such as Europa and Enceladus, also attract the attention of scientists. Beneath their icy crusts, there may be oceans of liquid water potentially capable of supporting life. The water geysers observed on Enceladus, ejecting plumes into space, indicate the presence of a subsurface ocean that might be heated by hydrothermal vents on the ocean floor. These conditions could be analogous to those that existed on early Earth, representing potential niches for life. However, the search for life is not limited to the solar system. Thanks to advances in astronomy, scientists have discovered thousands of exoplanets, planets orbiting other stars. Some of these exoplanets are located in the so-called habitable zones, where conditions might be suitable for the presence of liquid water. An example of such a planet is Proxima Centauri b, which orbits the star Proxima Centauri, the closest star to us beyond the solar system.
The search for life on these exoplanets involves not only observing their atmospheric characteristics, but also searching for biosignatures, chemical traces that could indicate the presence of life. Molecules such as oxygen, methane, and ozone might suggest biological activity if found in significant quantities in the atmospheres of these planets. Current and future telescopes, such as the James Webb Space Telescope, will play a crucial role in searching for these biosignatures and understanding the potential for life beyond Earth.
One of the most intriguing questions regarding extraterrestrial life is the so-called Fermi paradox, named after the physicist Enrico Fermi. The question Fermi posed is simple: where is everybody? If life is widespread in the universe, why do we not see any signs of other civilizations? This question has led to numerous theories and speculations about the nature and fate of intelligent life in the universe. There are various answers to this question. One hypothesis suggests that intelligent life in the universe may be extremely rare. Perhaps the conditions necessary for the emergence of intelligent life are so specific that they only occur on a few planets. Moreover, even if intelligent life does emerge, it may not last long due to various threats such as global catastrophes, self-destruction, or technological barriers.
Another hypothesis proposes that advanced civilizations might be avoiding contact with us or using technologies that we have not yet detected. This idea is known as the zoo hypothesis or cosmic quarantine, suggesting that more advanced civilizations might deliberately avoid contact with us, observing us from afar, or even hiding their presence. Perhaps they consider us not yet developed enough for contact or fear interfering with our natural course of evolution. Another theory suggests that we are simply not looking for the right signals or not searching actively enough. Most of our attempts to detect extraterrestrial civilizations are based on radioastronomical observations, but advanced civilizations might use entirely different means of communication or technologies that we have not yet discovered. The Big Bang model gets stronger with each early huge galaxy that Webb finds. As a way to make sense of the results, scientists suggested that early galaxies might have been more efficient than modern ones, for example, by using their gas stores more quickly. But that just puts things off. How could that level of efficiency appear so quickly, in such large numbers, and over such large areas of the early universe? Also, why didn't models say it would happen?
Another theory suggested that perhaps dark matter clumps in the early universe created deep potential wells, allowing matter to collapse faster than expected. But even this trick struggles to explain the sheer number of massive galaxies Webb has found. And it doesn't account for the metallicity and organized structure seen in so many of them. If the timeline of galaxy formation is off, it might mean our measurements of distance, based largely on redshift, need to be re-examined. It might also mean that time in the early universe functioned differently than we assume, or that the cosmic expansion model itself needs updating. Perhaps the laws of physics we observe today didn't hold exactly the same way when the universe was young. These questions are now rippling through astrophysics, like shockwaves. The standard model of cosmology, known as LCDM, lambda cold dark matter, has long been considered robust. It accounts for expansion, the cosmic microwave background, large-scale structure, and more. But James Webb's findings are testing the edges of that confidence. Some scientists have even called the early results a crisis in cosmology, one that demands either serious revision or radical reinterpretation. Meanwhile, the Webb telescope continues to deliver. Every new image, every deeper exposure seems to reveal yet another galaxy that's too big, too old, or too fast to fit the timeline. And while researchers are hard at work refining measurements and testing alternatives, the broader picture is hard to ignore. The early universe looks far more like a cosmic metropolis than a construction zone. It's still too soon to say whether these discoveries will overthrow the Big Bang theory entirely. Paradigms don't collapse overnight, but history shows us that when observation contradicts theory, the burden is on the theory to adapt.
Redshift reconsidered. One of the most important ideas in astronomy is the idea of redshift. It tells us how far away something is in space. That's how we plot time. And it's the very thing that tells us how far away and how far back in time a galaxy is. But now that James Webb has found new things, some scientists are starting to wonder, did we get redshift wrong? To understand the weight of that question, you first have to understand what redshift is supposed to tell us. When light travels from a distant object through the expanding fabric of space, it stretches. Just like the sound of a receding ambulance lowers in pitch, the wavelength of light increases as its source moves away from us. Blue light becomes redder, hence the term redshift.
In cosmology, redshift is also used to track cosmic expansion. The higher the redshift, the farther away the object is, and, crucially, the further back in time we're seeing it.
An object with a redshift of 2 is being observed, as it was when the universe was roughly 3 billion years old. An object at redshift 10, that's from when the universe was less than 500 million years old. The higher the redshift, the closer we are to the Big Bang. We use this relationship to build the entire cosmic timeline, from the formation of stars and galaxies, to the appearance of black holes, even to the rate of universal expansion.
In essence, redshift isn't just a measurement. It's the backbone of cosmic history. The galaxies observed at extreme redshifts, values of 10, 11, 12, and beyond, aren't behaving as expected. They're too big, too evolved, too structured, as if they've had far more time to grow than the timeline allows. One explanation is that these galaxies are somehow younger than they appear, that their brightness, mass, or structure is misleading. But another, more radical possibility is that our interpretation of redshift is flawed. Could it be that redshift isn't telling us what we think it is? That perhaps cosmic expansion isn't the only, or even the correct reason for why light gets stretched over vast distances?
This is not a new question. In fact, it's one of the oldest controversies in cosmology. When Edwin Hubble first saw that galaxies were redshifted and looked like they were moving away from us in the early 1900s, some scientists came up with other ideas for why this might be happening.
The tired light theory was one of the most famous. It said that photons lose energy by interacting with particles or fields in space, which makes them redder. In that view, redshift would not show that something is expanding, but that photons are getting tired after traveling long distances. That theory fell out of favor for lack of supporting evidence and for failing to match certain observed features of the universe, like the precise spectrum of the cosmic microwave background. Still, Webb's findings are giving new life to old questions. If expansion alone can't explain the strange maturity of high redshift galaxies, is there something else affecting how we interpret redshift?
On a higher level, there are also theoretical theories that question redshift. Some scientists think that space-time might not be smooth, especially in the beginning of the world. Light might have redshifted in ways we don't understand right now, if space-time curves or quantum fluctuations were stronger in the past. Others say that light might combine with dark matter or energy in ways that change its frequency over billions of years. Still others point to the possibility that light behaves differently at quantum scales, meaning redshift could be influenced by factors that aren't part of the standard model at all.
If space is granular, if time is emergent, or if the speed of light itself has changed over cosmic history, then everything we assume about redshift might be built on a moving foundation. There's also the unsettling realization that much of our redshift calibration depends on models we're now questioning. We use redshift to estimate distance, but we also use models of galaxy evolution to infer redshift. This circular logic becomes dangerous when the very models that interpret redshift are being challenged by the Webb data. It's too early to throw out redshift entirely. The idea remains one of the most predictive and consistent features of cosmology, but the precision with which we equate redshift to time and distance may need recalibration. It might be that redshift does indicate expansion, but not in a linear one-size-fits-all way, or that in the earliest epochs, something unknown distorted the relationship we've come to trust. The impossible stars. The first generation of stars, the so-called Population 3 stars, were supposed to be seen by the James Webb Space Telescope. These stars are big, hot, and mostly made of hydrogen and helium. These were supposed to be the first light sources in the universe. They were supposed to have been born in a world that was clean and free of heavy elements. Instead of finding the long-thought-to-be primordial stars, Webb has found something very different, stars that shouldn't exist that early, and formed in a way that doesn't fit with the normal model of cosmology's timing and chemistry. What Webb found were massive, luminous stars embedded in ancient galaxies, radiating intensely not just with hydrogen and helium, but with clear signs of metallicity.
In astrophysical terms, metals refer to any element heavier than helium, carbon, oxygen, nitrogen, iron, all of which are formed in the hearts of stars and scattered by supernova explosions. The presence of these elements in early stars implies that several generations of stellar birth and death had already occurred, but Webb is seeing these enriched stars just a few 100 million years after the supposed Big Bang. That leaves almost no time for multiple generations of stars to live, die and recycle their materials into more complex offspring.
It shouldn't be happening under the Big Bang framework. The first stars form after cosmic recombination, when electrons and protons combine to form neutral atoms, and the universe cooled enough for gas to clump under gravity. These population-free stars, if they existed, would live short, violent lives, exploding in brilliant supernovae and paving the way for second and third generation stars enriched with heavier elements.
But this process takes time, hundreds of millions of years, if not longer, to build up the levels of metallicity we're seeing in stars that appear to exist. Webb's discovery of stars with high metallicity at such extreme redshifts poses a serious problem. It doesn't just suggest early star formation, it suggests early chemical evolution at a speed and scale that current models can't replicate.
In galaxies like GNZ 11 and CS 1019, stars appear to be not only burning hot, but chemically complex. That complexity requires a stellar life cycle that should be impossible within such a short cosmic window. Some experts have tried to explain this by saying that stars formed very quickly in the early universe. It's possible that the conditions in the very first galaxies made it possible for stars to form, live, and die much more quickly than was thought before. They might have been denser, cooler, or had crashes caused by shock waves that start the chemical cycle right away.
But this idea isn't logical because Webb isn't just finding one richer star or galaxy, it's finding a lot of them. This common trend makes it seem like the early universe wasn't a blank canvas, just waiting to be drawn, but a scene that was already full of details.
What's even stranger are stars that are too big for existing theories to understand. Based on Webb's findings, some of the stars may have masses hundreds of times bigger than our Sun, which could be close to the theoretical upper bounds. The usual view is that big stars are unstable, and the radiation pressure should break them apart or make them fall into black holes. But in the early galaxies Webb looked at, huge stars not only seem possible, but also common. These impossible stars shine with such luminosity and complexity that it's hard to imagine them forming without some precursor conditions. But there shouldn't have been enough time since the supposed origin of the universe for those conditions to exist. Even accounting for gravitational collapse and rapid cooling, the interval between the Big Bang and the formation of these stars is alarmingly short. What if the universe didn't start with simple hydrogen clouds and a clean slate? What if instead the early universe was already chemically active, already building stars with metals, already forming systems more advanced than we expected? That would suggest a very different origin, or at least a different pacing than the Big Bang theory allowed.
Some strange ideas like plasma cosmology or steady-state models say that the universe is endless or circular, and that matter and energy are always changing instead of being created in a single event. These points of view say that early stars aren't really early, they're just a part of a process that happens over and over again in the universe. These models haven't been used in a while, but Webb's results are giving them some attention again. There's also the chance that our entire model of stellar evolution is missing something. Perhaps the physics of the early universe allowed for faster fusion, quicker lifespans, or exotic stellar behaviors we don't yet understand. Maybe dark matter played a catalytic role. Maybe there's an unknown factor influencing how stars are born, live, and die.
But until those gaps are filled, we're left with a universe that seems to be cheating the rules. The stars that were supposed to be impossible, too massive, too old, too enriched, are not only real but common, and they're rewriting the story of how light returned to the cosmos.
Ancient black holes.
Where there should be none. People often think of black holes as the grim reapers of the universe. They are the dense, collapsed remains of very massive stars or the enormous monsters that lurk at the centers of galaxies. Their birth is not simple or quick. Black holes are thought to be the end of time in the standard model of astronomy. To form, live, and die, they need generations of stars. They want mass, mergers, and brutal, slow construction. They are, however, being found everywhere by James Webb. Way too early and way too big. Supermassive black holes, those with millions or even billions of times the mass of our Sun, are normally associated with well-evolved galaxies. Our own Milky Way hosts one, Sagittarius A, sitting calmly at the center, a gravitational anchor that formed over billions of years. But Webb's observations are detecting active galactic nuclei, AGN, the bright energetic signals of material spiraling into black holes in galaxies that exist less than 700 million years after the Big Bang.
Some of these black holes already appear to have masses in the hundreds of millions of solar masses, and that timeline is a problem. This is not something that can be done quickly. It takes time. Even if you start with a seed black hole, which would be the remains of a very large population 3 star, maybe 100 solar masses, it would have to keep growing through accretion and collisions with other galaxies in order to become supermassive. It takes hundreds of millions to billions of years for that process to finish, even in the most hopeful models. Webb, on the other hand, sees them fully grown before the universe was formed. This isn't just early black hole formation, this is early black hole domination.
Some of the host galaxies appear to be centered around these giants, suggesting that black holes were not just a consequence of galaxy formation, they may have been a prerequisite. That flips the traditional model on its head. Sears is one of the most shocking examples. It is a live galaxy with a giant black hole that was around when the universe was about 570 million years old. Even more amazing is that it looks like it is accreting matter, which means it wasn't inactive and was actively eating gas and changing its surroundings. This is the kind of behavior that galaxies usually show when they are much further along in their growth.
Some scientists have proposed that these black holes formed from direct collapse, an alternative mechanism where massive clouds of gas collapse directly into a black hole without ever becoming a star. This would create larger seed black holes from the start, allowing them to grow more quickly. But even this theory struggles to explain how such seeds could be in place and already accreting so early, especially in galaxies that are also forming stars rapidly. To grow so quickly, these early black holes would need not just mass, but an abundant fuel supply, cold gas, dust and matter falling in at just the right rate. But such smooth, rapid feeding contradicts many of our models, which assume turbulence, feedback and fragmentation would slow the process. And yet Webb is finding these monsters already formed and active, quietly violating every timeline we thought we understood.
Even more concerning is the number of early supermassive black holes. They're not rare gems. They appear to be common features of early galaxies. That implies a universal process, not an exception. And that in turn suggests something far deeper might be wrong with our assumptions. If black holes this massive existed so early, it changes how we understand structure formation, star formation, and even reionization, the process by which the first light sources transformed the universe's opaque hydrogen fog into transparency. Black holes, through their energetic radiation, may have played a far larger role in shaping the early cosmos than previously thought. Some people are even starting to think that black holes might not be the end of evolution, but the beginning. Some models now think that primordial black holes,
which didn't form from stars but straight from quantum changes in the very early universe, might have been the first things that led to the formation of galaxies. Black holes didn't wait for galaxies to form around them. In this version of events, it was around the black holes that the galaxies formed. It's an unsettling reversal, and it forces cosmologists to confront uncomfortable possibilities. If supermassive black holes are this ancient, this common and this central to galactic life, then maybe our universe didn't evolve in the slow, linear fashion we imagined. Maybe it sprang into complexity faster than we thought possible. Or maybe it always had.
Dark matter in crisis. Dark matter has been the universe's quiet framework for decades. It is the mysterious material that makes up more than 80% of all matter in the universe and holds galaxies together. It does not give off light, reflect light, or interact with the electric force. But its pull on the universe can be felt everywhere. That's what we thought anyway. The James Webb Space Telescope is here. Webb's study of the universe's oldest galaxies and structures has not only raised questions about how old and how big these things are, but it has also started to question the framework that these things are meant to hold together. However, when we use dark matter models on Webb's data, we find something very troubling. The math doesn't add up. The standard cosmological model known as LACDM, lambda cold dark matter, relies on the idea that dark matter clumped together early in the universe, creating gravitational wells into which normal matter could fall. This clumping is what supposedly triggered the formation of galaxies, stars, and eventually planets. Dark matter wasn't just a background player, it was the first actor on the stage. But Webb's observations are now suggesting that large, well-structured galaxies appeared far earlier than ACDM allows. If these galaxies had dark matter halos, which they must, according to the model, then those halos would need to form extremely rapidly, more rapidly than the model permits. In other words, if dark matter was doing its job in the early universe,
It was doing it too fast. On the other hand, Webb's observations of some galaxies show that they depend less on dark matter than was thought. The spectral data we use to figure out their mass distributions and spin shapes don't always match up with what we would expect from dark matter. These galaxies act like they're held together by less unseen matter than the model says they should be.
This isn't the first time dark matter has raised eyebrows. Even in the nearby universe, some galaxies like NGC 52 DF2 have appeared to contain virtually no dark matter at all, defying the expectations of galactic formation theory. But these were rare, localized puzzles. What Webb is showing is that the earliest galaxies, supposedly shaped entirely by dark matter, are not behaving as dark matter-dominated systems should.
The way the structure is spread out is another point of tension. It takes time for dark matter to gather into clumps in CDM. In the beginning, the universe should have been mostly smooth, with small changes over time turning into strands, nodes, and gaps. But Webb is finding galaxies that are not only closer together, more lined, and sometimes more orderly than theory says they should be. Without highly developed dark matter support, there shouldn't be this much order. But where did the order come from if the dark matter didn't have time to set itself up in those ways first?
Perhaps dark matter behaves differently than we thought. Maybe it's not as cold as LCDM suggests. If it's warm or self-interacting, it might clump faster or distribute itself differently. But these modified versions of dark matter create their own problems and don't fully align with other observations, such as those of the cosmic microwave background or galaxy cluster dynamics.
Second, it may mean that alternative gravity theories, long considered fringe, need to be re-examined. Models like MOND, modified Newtonian dynamics, or TAVIS, attempt to explain galactic rotation and structure without invoking dark matter, instead modifying how gravity works at large scales. These theories have struggled to explain all observations, especially on cosmological scales, but Webb's revelations may provide new ground for hybrid models that blend modified gravity with limited dark matter.
Third, and perhaps most radically, It could mean that dark matter, as we conceive it, simply doesn't exist, or at least not in the form we've theorized for nearly half a century. Maybe our gravitational equations are incomplete. Maybe our understanding of mass and energy in curved space-time is flawed. Or maybe we're missing a layer of physics entirely, one that Webb is beginning to expose, not with direct evidence, but through persistent mismatch between prediction and reality. The most important thing about this problem is that dark matter isn't just a placeholder in our models. Modern astronomy, astrophysics, and particle theory are built on top of it. In some ways, it even explains how galaxies form and how the universe is structured. Dark matter is needed for the dominoes to fall. If it fails, dark matter is not being directly found by James Webb. It can't. But by pushing the edges of what can be seen in terms of time and resolution, it is trying. What would happen if dark matter existed, and those effects are looking more and more stressed?
So, cosmic inflation. Far reconsidering cosmic inflation. For a long time, cosmic inflation has been seen as one of the best ways to explain the universe. It was a bold addition to the Big Bang theory when it was first put forward in the early 90s. It wasn't part of the original framework, but it was needed to fill in some of its biggest gaps.
The main idea behind inflation is that the universe grew very quickly and exponentially just a few fractions of a second after the Big Bang. Space grew bigger than the speed of light for a very short but important moment, stretching the universe flat, smooth. Inflation was introduced to solve problems.
The horizon problem, for example. Why does the universe look the same in every direction, even though distant regions shouldn't have had time to exchange light or information? Inflation says, because those regions used to be in contact until inflation blew them apart.
Then there's the flatness problem. The universe appears to be geometrically flat, which should be extremely unlikely. Inflation says that's what happens when you inflate a small, curved patch of space. It flattens out. Neat, clean, mathematically clever.
But there's one thing inflation didn't do. It didn't make any direct, testable predictions when it was first proposed. It was speculative, and for years, it remained on shaky ground. Later refinements gave it more mathematical rigor, and its predictions, especially about the spectrum of cosmic microwave background fluctuations, lined up remarkably well with observations. That cemented inflation's role in the cosmological mainstream. It became standard doctrine.
However, inflation has always had a strange air of creativity about it, a fix on top of a workaround. With the help of early data from James Webb, the questions that inflation was meant to hide are now coming up again.
Webb isn't looking at inflation straight on. That event would have happened about 10 seconds after the Big Bang, which is so early that not even light had come into being yet. But Webb is looking at the shape of the universe in its early stages, which is a result of that time of inflation. We notice that the building looks too well put together, too perfect, and sometimes too old.
The more we see of it, the galaxies that Webb is detecting aren't just forming earlier than expected. They seem to appear fully formed, with large masses and ordered spins, as if they didn't evolve through chaos at all. This is problematic because inflation was designed to explain structure by introducing small quantum fluctuations into a smooth early universe. These fluctuations then seeded the growth of galaxies, stars, and clusters.
But what happens when that structure appears almost instantly without enough time for fluctuations to evolve? The paradox is reversed. Inflation was meant to introduce just the right amount of irregularity into a very smooth universe. But Webb's early galaxies seem to skip the irregularity entirely. They suggest a universe that went straight from inflation or something like it into complexity. That either means inflation operated very differently than we thought, or it didn't happen at all. Inflation predicts a very specific spectrum of fluctuation, with certain sizes of structure being more common than others. Yet the cosmic web, even at early times, seems to exhibit a puzzling uniformity, one that doesn't align neatly with inflation's output.
If that trend holds, it could indicate a deeper inconsistency between the predictions of inflation and the universe's observed evolution. On top of that, there are philosophical problems. Even though inflation is useful from a mathematical point of view, it has worrying effects. A lot of the time, this leads to the idea of a multiverse, which means that inflation didn't happen just once, but keeps happening forever in some places, creating an infinite number of tiny worlds. By definition, these worlds can't be seen. That means the theory is very hard to disprove and very close to philosophy, which is a very bad thing. Webb's findings bring us back to a crucial question. Did the universe really need a brief moment of unthinkable expansion to explain its current state? Or were we using inflation to cover for gaps in a model that never worked as smoothly as we believed?
Some researchers are beginning to revisit older ideas, like bouncing or cyclic cosmologies, where the universe didn't start from a singularity at all, but from the collapse of a prior universe. Others are exploring quantum gravity frameworks, where space and time are emergent phenomena, and the need for inflation disappears entirely.
The Big Bang model. It was thought that the early universe would be mostly smooth, but with some small flaws caused by quantum ripples that were stretched into small changes in density. These tiny variations were critical. They were supposed to be the imperfections that allowed structure to form. A completely smooth universe, after all, would remain smooth. Galaxies need gravitational irregularities, bumps and clumps of matter to pull together gas and stars. Without these flaws, there's nothing to assemble into stars, planets, or us.
In fact, these imperfections are visible in the cosmic microwave background, CMB, showing up as faint temperature fluctuations, the fingerprints of those early seeds. The CMB shows those tiny changes as expected, but James Webb's pictures of the early universe don't seem to show the chaos that those seeds should have caused. Webb is looking at a universe that is too smooth, too symmetrical, and too calm to find signs of a universe that is still putting together its structure. This isn't the ease that comes from being the same everywhere. It's not that galaxies are spread out evenly. They're showing up in places, numbers, and shapes that are hard to predict. It's more that the rate and organization of structure creation look too clean and advanced for how soon after the Big Bang they're happening. Galaxies are showing up with spins that are in order. Clusters are coming together in a very consistent way. Things aren't as messy as they should be, which is disturbing.
According to the inflationary model, the fluctuations should have produced clumpy distributions in the early stages of the universe. Regions of higher and lower density gradually collapsing into increasingly complex arrangements. Webb, however, is detecting galaxies that seem to have bypassed the chaos. In some fields of view, there's a surprising uniformity in size and shape. Structures that should have formed over billions of years seem to be already in place, just a few 100 million years after the Big Bang.
This problem is similar to what some scientists have said about inflation, that it fixed too many problems that were present in the world at the start. Inflation may have made the universe too smooth by stretching space so quickly and efficiently, leaving not enough room for structure to grow in the way we see it. The galaxies we see with Webb shouldn't exist, if that's the case. Still, there they are. Some have proposed that our understanding of early gravitational collapse might be flawed. Perhaps gas and dark matter coalesced faster than expected. But this too has limits. Gravitational systems need time to grow. Even if you crank up star formation efficiency or hypothesize unusually cold dark matter, it doesn't easily account for the scale of the structure being observed.
Others point to the possibility that our cosmological simulations used to predict how structure should have formed may be oversimplified. Perhaps the universe doesn't evolve the way we've been programming our models. But if that's true, it calls into question the reliability of decades of predictions built on those models, including the very shape of the early universe. There's also the potential that the smoothness is an illusion, that we're seeing galaxies that formed unusually early due to unknown physics, while the rest of the universe lagged behind. But the more Webb surveys the early cosmos, the harder this is to sustain. The anomalies are becoming too common to be rare flukes. Another cosmic puzzle that is related to the too smooth problem is, why is the structure of the universe on a big scale so perfectly balanced? How is it that the rate of growth, the spread of matter, and the curvature are all so perfectly lined up for galaxies to form in the first place? Scientists thought that inflation would explain this, but Webb's results show that the accuracy might be even higher than inflation suggests. It's almost like the world knew exactly what it was doing.
What if the early universe wasn't a mess that eventually birthed order, but something closer to a ready-made system? A cosmos that didn't build complexity, but began with it already encoded? That would require a reimagining not just of structure formation, but of the universe's initial conditions, or the absence of a singular beginning altogether.
James Webb, the impossible early galaxy problem. It was only a matter of time before someone said they were impossible. This can't be meant in a poetic or figurative way. It's just not possible according to normal physics. The James Webb Space Telescope's first deep field pictures showed these galaxies that don't look like they should. They are too big, too bright, too old, and most unsettlingly, there are too many of them for any place on the Big Bang time frame to fit.
Astronomers expected Webb to find primitive objects, small, chaotic, gas-rich clouds in the process of becoming galaxies. They expected to see the messy beginnings of order, stars just igniting, and structures forming slowly over hundreds of millions of years. What they found instead were fully formed galaxies, shining at redshifts of 10, 12, and even higher, galaxies that existed when the universe was just a few 100 million years old.
These galaxies weren't merely surprising because they were there. They were impossible because of how much they had already accomplished. Some contain as many stars as the Milky Way, others have well-defined disks, stable rotations, and chemical enrichments that suggest they had already undergone several generations of stellar evolution. They didn't look like babies, they looked like adults, living in a toddler universe.
Webb saw a galaxy called Sirius 9316 that has a redshift of about 16.7, which means we are seeing it as it was only 240 million years after the Big Bang. This is one of the most striking cases. Models that are already out there say that this galaxy shouldn't have had enough time to make even its first set of stars, let alone grow up. Still, there it is, clear, organized, and shining.
The reason these galaxies are labeled impossible isn't just because they're early, it's because the timeline for how long it takes to form stars, build mass, and organize into complex structures is grounded in well-understood physics. Gas clouds take time to cool and collapse. Star formation requires density thresholds and gravitational instabilities. Metal enrichment requires the birth and death of multiple generations of stars. These are not processes that can be rushed.
And yet somehow, these galaxies seem to have done it all within the first 2% of the universe's lifespan. When Webb began returning its early data,
Many assumed that some of these galaxies were being misidentified, that their redshifts might be overestimated due to photometric confusion or contamination by nearby objects. But as the spectroscopic confirmations began rolling in, the reality set in. These redshifts were real, and so were the galaxies.
This has led to a growing chorus within the astrophysics community. Something about our model is broken. Some theorists have proposed revising star formation rates, assuming these early galaxies were much more efficient at converting gas into stars than modern ones. Others suggest a new class of ultra-dark halos that might have accelerated collapse.
But these patches only go so far, and they raise new problems. If star formation was that efficient, why don't we see similar behaviors in more recent cosmic history? If mass collapsed that quickly, what does that say about the nature of dark matter or the influence of unknown forces? And perhaps most fundamentally, why didn't our models predict this? That's the question that keeps resurfacing. For decades, cosmological simulations have guided our expectations for what the early universe should look like. We built a framework, the LCDM model, that told us when galaxies should form, how large they should be, and how they should evolve.
But Webb has pulled back the curtain and revealed a stage already full of players before the play was supposed to begin. It's not just that these worlds are there that makes people feel uneasy. It means that our whole idea of how the universe is put together may be wrong in terms of time.
What else did we get wrong about the early universe? If it wasn't a slow build-up of complexity, but a quick jump into it?
No time for evolution. Why the early universe looks ready-made.
Modern astronomy is based on the idea that things get more complicated over time. Galaxies don't just appear like light bulbs turning on, they change over time. They begin as clouds of hydrogen and helium, stick together because of gravity, give birth to their first stars, get more material through the death of stars, and slowly change into the moving structures we see today. It is thought that this process of the universe growing up from simple to complex will take billions of years.
But the James Webb Space Telescope has a different view. One in which the early universe didn't change slowly over time. It came into being fully formed.
In every deep field image, James Webb is finding galaxies that look complete, not on their way to becoming something, not assembling already there, with star formation rates that rival modern galaxies, with disks, bulges, and spiral arms, with chemical signatures that suggest multiple generations of stellar recycling. These aren't rough drafts, they're polished chapters, appearing just a few 100 million years after the supposed Big Bang.
According to our models, the cosmic dark ages, the period between the release of the cosmic microwave background and the first stars, should have lasted around 200 to 300 million years. During this time, the universe was cooling and gravity was slowly beginning to work on the first neutral atoms. After this phase, the earliest stars and galaxies were expected to begin forming, messy, metal-poor, and small.
But what Webb is showing instead is a universe that seems to have skipped the awkward adolescence altogether. Some of these galaxies have stellar masses comparable to the Milky Way. That means they would have needed to form stars at breakneck speed, turning gas into suns with an efficiency that no current model supports.
Even the most aggressive starburst scenarios, events that trigger rapid star formation, can't explain how galaxies this big could exist this early. If galaxies form so quickly and completely, it means our timeline for cosmic evolution is wrong, possibly by orders of magnitude.
It raises the uncomfortable possibility that the universe wasn't a slow unfolding narrative, but something preloaded with structure, just waiting to be observed.